Okay. So the question goes like this. You have a matrix of zeros and ones. So the numbers in this, I mean, they're just binary digits of 0 and 1. Okay, those are the elements of the matrix. So Aij is going to be either 0 or 1. And this is the matrix A. Okay, it has n rows and m columns. Okay, let's put some examples here. 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0. Okay, so this is the matrix that we have. What we need to do is find all submatrices rather, such that they have all zeros as elements. Okay, so if I take the submatrice of row 0, 1, 2, so row 2 and column 0, 1, so up to, so 2, 1, up to the, this is column 2. Okay, so column 2 will come over here. My drawing is not so good. That's okay. Up to 4, 2. So you can see this rectangle. Basically, this is one submatrix which is inside the matrix, which has all zeros. Okay, so we need to find all of the submatrices, like basically give a count of all the submatrices which have all zeros inside them. Okay, submatrices. Yeah, these terms are a little difficult, but I'll try my best. But this is the problem. I'll give you guys 5 minutes to ask doubts on this and think of a solution before I start getting to the solution. In fact, I'll give you the brute force solution so that things get a little simpler. The brute force solution is for every starting point. Okay, basically, we need to find the submatrices, which means that we need to find rectangles in this large rectangle such that all the elements in them is 0. So what are the possible rectangles you can have? You can have for every starting point and every ending point, you can take the sum of that submatrice and then see if you're getting zeros. So for every starting point, I'll just write this a little more neatly. And in that, for every possible ending point, okay, for this corresponding starting point, if the rectangle that you just created using the starting and ending point is equal to 0, is full of zeros, then count plus plus. Okay, so as you can see, this is a totally brute force approach. For every starting point, how many starting points do you have? N cross m. Okay, every point here, this is one starting point, this is one, this is one, this is one. So if you count the total number of them, there will be n rows and m columns. And similarly, how many ending points do you have? You have n cross m. Okay, they will be reducing according to the starting point, but effectively, if you take the order complexity, this will turn out to be order n square into m square. Okay, and all the elements in this have to be 0. So I'm assuming that we have a fast way of finding it. Otherwise, if you do it the brute force way, this is going to be order n cube, n cube. Okay, so this is totally off limits. But yeah, that's the absolute brute force approach. So maybe I should note that down. Like this is one easy way to get rejected in an interview, but this is the absolute brute force approach. Can you think of something better? Okay, it's 5 minutes. I'll be answering questions till then. Let me know in the comments now. Oh, there's people from LinkedIn also. Hi, hi Rajesh. Hi. Okay. So Shivang Saxena, the matrix can be a square, but it is a rectangle, n cross m, and we need to find all the submatrices, which is basically rectangles inside this rectangle, such that all of the elements in them are 0. Oh, I don't know if you guys can see the GKCS, but yeah, okay, I'll just cover it up. Yeah, some kind of DP, I guess. Yeah, but which kind of DP, Pratyush? So, okay, can we take overlap submatrix in result? The basic question is this: you have a rectangle of size n cross m, and you need to tell me how many rectangles inside this rectangle. Okay, starting from ij and ending at kl. Okay, basically that's what a rectangle is, right? You just define two vertices, and that's enough to define a rectangle. How many of them have all zeros inside them? Can you give an algorithm? The brute force algorithm has been explained over here. Every starting point, every ending point, take that rectangle, find if that rectangle is filled with zeros. Okay, so you can do a simple scan in that, like a raster scan, go straight. And then if you see that that rectangle is full of zeros, increment the count plus plus. So the total order complexity of this is going to be something like n cube n cube. Okay, if you take a square matrix, then that is n raised to power 6, which is massive, which we cannot allow. So now we're going to try to break down the problem so that we can, find a solution efficiently. Quite a few people are talking about dynamic programming. That's the right approach. I've already mentioned it. But what kind of dynamic programming are you going to do? I once went to this college. I won't name the college, nor will I name the student. But I was there as an interviewer, and there was this guy. He was like, "I think I should use dynamic programming in this question. Not this question specifically, but there was another question." And I said, "Okay, then do it." So the guy was thinking for a while. Then he said, "Maybe I should try a greedy algorithm." I thought about, dude, you're just throwing terms around. Like, why don't you try to solve the problem? Of course, I didn't say this. I just quietly waited till the timer timed out. Guy got rejected, unfortunately. But yeah. Sometimes you have a good intuition of what's going to happen, how to go ahead and solve the problem, but then you also have to like get into the groove and actually solve the problem. Okay. That anecdote actually probably made me lose quite a few. Good questions. Is 1 cross 1 also counted? Yes. Since that is also counted. Mansi Gupta is saying this is the island problem. No, this is a little more, it's a little different, I think. It's a little more complex. You have to find every rectangle which has full zeros. Okay, but the island problem might give you some clues. Largest rectangle ending at a cell such that all elements are 0 using DP. Right, BBU. So, but how are you going to implement it? Like, okay, I get it. Yes, that's what you want. Is n cross m cross m? Okay, Nanda Kishore, that's a good attempt. So we already have something which is horrible, right? N cube m cube. You are saying n m square. Let's go for it. Yeah, go ahead. Let us know what that solution is. So, okay, there's quite a few people who are guessing. Treat this like a real interview if you can, because in the real world, you can't look at the interviewer's face and say, I guessed it. So, go for it. Yeah, this is a good one. Can be done in order n, m, minimum nm. Are we looking for a better solution? No. Why don't you mention the solution? Maybe we can see if we can do better. Order n square BBU. Okay, I don't think that's possible, but go for it. How are you going to do order n square? Order n square. Okay, I mean order m n, right? Because you will read the matrix once. I don't think that is possible, but go for it. Okay. So firstly, I'll just kind of move forward with a part of the question. Firstly, n square m square is not very efficient. Like it's horrible rather. So what are we doing? We are taking the sum of this rectangle, right? And we are trying to see if it's full of zeros. So one way to quickly calculate a sum given a starting point and an ending point in a matrix when you're doing it multiple times is to use dynamic programming. Now, how do you use dynamic programming in this particular case? So take this rectangle. Okay. Now, effectively, this is your original rectangle. This is a rectangle whose sum you want to find, okay? Because you're doing this for every starting and ending point. Okay, so assume that this is one of the starting and ending points that you have. Now, to find the sum of this rectangle, this is the shaded region, right? Effectively, what you need to do, this is a common idea for dynamic programming, is take this whole sum, this entire shaded region, and then subtract out 3 parts from it, or rather 2 parts from it. So those parts are this. This is one part that you have to subtract out. Okay. This is another part that you have to subtract out. Right. So those are 2 parts. And finally, because you subtracted this twice, you have to add it. So instead of subtracting there, we add it back. Just give me a second. Clicking sometimes is difficult. Okay. So this is added back. So effectively, if you want to find the sum of a rectangle having a starting and an ending point, what you need to do is you're going to get the sum of the rectangle from 0, 0, so origin over here, up till ending point, that is the full rectangle, minus this bit that we said, right? Those 2 red rectangles that we have. So sum of a rectangle from this point, the origin, to this point. So that is over here. You have the ending points x-axis, and over here you have the ending points y-axis. Okay, so I'll just make this simpler. So I'll call this S1, S2, and I'll call this E1, E2. Okay, these are the coordinates, and this is 0, 0. So effectively what we have is get me the sum of the rectangle S1, S2, E1, E2. Okay, for that I need to get the sum of 0, 0 to E1, E2 minus sum of 0, 0 to S1, E2 minus sum of 0, 0 to E1, S2 plus sum of 0, 0 to this thing over here. Okay, so S1, S2. Okay, this part is very easy. This is just to get you in the groove. What's happened here is because I can take this sum up to any point from origin in just one shot using this formula. Okay, how is this helping me? How is this formula helping me? Basically, this thing you are seeing is redundant. It's everywhere. So all we need to do is take the sum of all rectangles from origin up till this point, up till all the points that you have in the rectangle. Okay, so I'll be sharing a link right now in the comments. You can use that later on to find how this happens. Like I said, this is an advanced question, so I don't want to go through the sum of rectangles dynamic programming. So that is Arden Dirtart. Okay, sum of angles. This is where you can find the problem. But like I said, this part is a prerequisite. if you can find sums efficiently this way, basically getting rid of this stuff and converting, I mean, finding sums in order n cross m. Why is that? Because the number of distinct S1, S2, and even E2 you'll have is n cross m. So effectively what you have is, in this much time you'll find the sum. And the original question initially over here had n cube, m cube. Instead, we are finding sums very efficiently, right? This thing has been made efficient. So now we go to order n square, because this has become order 1. Okay, using this formula that we showed here. Okay, if this is a bouncer, like I said, I'll just share it right now. Yeah, Arden. This is like part 1 of the question. So if this is seeming very difficult, I would strongly suggest that you try this question later also. But this is the link. Do give it a go. Okay. Fine. So now we have reduced the time complexity from order n cube, m cube to order n square, m square. Why am I even explaining this? Because even in a Google interview, in any interview, you have to then explain them that this is what you're doing. You can't just say that I'm going to be using this formula of finding the sums. You have to go ahead and then show them this equation and then possibly even code it. So in the coding, there might be some mistakes that you can do. So, but it is one step. So the step 2 is to actually optimize this part of the solution. Okay. Right. So I'll give you guys 5 more minutes. And you guys can think about how to speed this up even more. You can't speed this up too much, but you can speed this up significantly. Rajesh Badam, no comment on LinkedIn from you. Yeah, I think that's a problem. I'll just share it on LinkedIn also. The interview ready page. Okay, I'm live on interview ready also. Good. So can I comment here? Yes. Thanks guys, I posted the comment. You can have a look. Okay, okay. We can use prefix sum for storing sum. Vishal Singh, you're pretty much hit the nail on the head. Can you elaborate on that? Okay, Nandakishore has an interesting comment. I'll just pick that in a minute. Before that, I'll just have a look at what are the other comments also up here. I might have missed some. Akash Kothepalli is asking what are the constraints. It's not mentioned, but in general, n square, m square is not great because it's rather, it's expected. It's easy, right? N square, m square is something that most of us know. Because if you're going to find the sums in order 1 for a rectangle, that's okay. I mean, so we are looking for something better than that. Okay, SM got the idea. Yes, we are creating a sum DP. That part is done. Maximum rectangle from lead code. This is one possible solution, Nitish. You can do, I think, something simpler. Okay. My approach will take order n square. I don't know. You haven't actually. That's not possible actually, BBU. You should try something else. Prashant Kumar Dikshit. We can find maximum rectangles for 0 and apply formula for How too many rectangles can be possible also. I think you're very close, LinkedIn user, but yeah, a little more detail will help. Find me, Nandakishore. Okay. Okay, I also have favorite people. Okay, got now. Space complexity, Aditya, is I mean, you can use order n cross m definitely because it's already being used in the matrix. You have auxiliary space. Okay, now BBU has changed it to order n cube. Okay. Kadani's algorithm. Okay. GitHub recently launched. Fine. Fine. I'll give you guys 1 more minute. Till then, let's read Nand Kishore's solution. Fix the row. Let I comma x and I comma y be the endpoints of the base. For this base, we can form rectangles from height 1 to min of height 1 to x to height 1 to y. Find height using prefix sums, column wise. Okay. Let I comma x. Let's try out Nand Kishore's solution. Let's see if that works. I would be very like, it's quite interesting. So let's head to the left over here. I have created a rectangle. Fix the row. Let it be I comma x and I comma y be the endpoints of the base. Okay. For this base, we can form rectangles from height 1. We can form rectangles from height 1, okay, to height minimum h of I x to h of I y. Yeah, that's a good idea. Basically, what you're trying to do is you're trying to create a shape. So it's a good idea, although it doesn't. I don't think it helps. It works. I tried it a few hours ago, and this seems to work. Basically, the idea is you have this rectangle, and then you can basically form a shape of ones which are creating a boundary. If I'm actually accurately representing a solution, Nandkishore, this is what I can understand. You're creating a boundary like a coast, and in this coast you can go up to a particular point, right? Then what happens is when you move forward, you reuse a lot of this coast. Okay, and then you keep moving forward in this like linked list fashion where you're reusing this coast and finding out the total number of rectangles you can create, because the maximum number of rectangles you can create from any point is going to be reducing as you keep going down. If that is the general idea. It has optimal time complexity and space complexity from what I understand. However, there's a much simpler way to do it. Okay. So if I've accurately represented your idea, that's a good idea. You can do simpler though. Okay. Order n square, m square. That might also be the case. You have to do a lot of optimization here to kind of bring down the time complexity. You need prefix sums here also. And then you have to like find, you probably need a priority queue. Basically that shape that is being created, the shape that we just created here, right? It has a minimum point and it has all this stuff in priority. So whenever you reach that point, you keep moving to the right. And whenever you reach that point, you evict it from the priority queue and you add the next point in the priority queue. So this might be the next shape. So this is the new shape. Okay, it's an interesting idea. However, I don't see it really helping in terms of the time complexity. Okay, so think about something which is even simpler, much simpler. Okay, let's go for the very simple solution then. Like very simple is subjective, but okay. So coming back to the question, this is what we have, and we are saying that for every starting and ending point, we need to check stuff, right? So let's see. This is the rectangle. For every starting ending point, find the sum. If sum is equal to 0, then count plus plus. No, I think we can do better. What can we do? the idea, I mean, how do we get here? Basically, you take a starting point and you fix that, just like Nankishore said. So I'll just unpin the comment. No, yeah. So you fix the starting point first. Okay, so x comma y is the starting point. So this is x comma y. And now what you do is you go as much as possible to the right. Okay, so this is still at coordinate y, but you are going to end up with x1. So x1 comma y. Okay, this is what you want to do. Initially, assume there's a linear scan. Okay, order n, doesn't matter. You somehow found a point where it is all zeros on the way. Okay, so if you had R1 zeros here, then how many rectangles can you make of size height 1? You can create R1 rectangles. Okay, you can create a rectangle with 1 0, a rectangle with 2 zeros, a rectangle with 3 zeros, so on and so forth. That's the idea. Similarly, what's going to happen is you're going to increase the height by 1. And now you had a 1 over here. That's the reason why you stopped, or you hit the end of the rectangle. Whatever be the case. For the next one over here, you do the same thing. You find as many zeros as you possibly can. The moment you hit that, the moment you hit a 1, you count the number of zeros you have here. Okay, so that is R2. How many rectangles can you make of height 2? R2 rectangles. Okay, you can have this one, so on till R2 rectangles. Similarly, you keep doing this till you either run out of zeros. By the way, remember that you can't have a bigger space here because there's a 1 here. So effectively, this is the starting point. You can't have an ending point over here. Impossible, because there's a 1 here. So the effective range keeps reducing all the time. At most, I mean, even if you have this free chunk of zeros, you're going to take the minimum of previous row, 0, and current. Okay, while moving forward. So effectively, what's going to happen is you're going to have at most this much. So even if you had the larger rectangle, you just take this much. Okay, so like this, you create some sort of a, effectively you've created some sort of a shape. Okay, and the total number of rectangles you can create for this starting point is R1 plus R2 plus R3 plus so on and so forth up to R of m. Or if it has n rows, then R of n rectangles. Okay, this part is simple. We just counted the total number of rectangles we can make for a given starting point. Right? How many starting points can we have? M cross n. And how many points are we crossing through? So we are doing this for every row. So that is into n. And we are running through one by one till we hit a 1 over here. So for every column also. So n cross n into n cross m. So that is still the old time complexity that we had here. So no improvement. But there is a clear possibility of improvement. Firstly, can you take the prefix sums of every row I? Okay, if this is row I, can you take the prefix sums of that? Why am I interested in doing this? Well, what is the prefix sum of the row up till this point? Let us assume that till now you have met 2 ones. Okay, so the prefix sum up till this point is equal to 2. If the prefix sum up to this point is equal to then 3, I mean, by definition, it has to be equal to 3 up till this point. Up till this point, it was 2. You didn't meet any 1. The moment you hit a 1, the prefix sum of that point will become 3. So effectively, you're looking for, you're doing some sort of a binary search in this array of prefix sums such that you get a 2. Okay, the largest element with 2 as the prefix sum. That's one way to look at it. An even simpler way, like this will probably be mind-boggling, an even simpler way is that you don't need to store prefix sums or anything. Just store the maximum number of zeros to the right of every element. So this element is x comma y, right? Find max zeros to right and keep an array like this. Okay, keep an array of, let's say, capital M of size n cross m. what it does is it keeps the maximum number of zeros to the right of every index. So how many do you have here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, that will be 8 for our x comma y. Okay. This part is simple. When you go down, what happened? X got incremented, y is just the same. This is all you need. Instead of going through one by one, you just take this value. Okay, and how are you going to populate this value? Brute force. It's okay. You have n cross m rows, and for every starting point, every point you're finding out maximum number of zeros you have on the right, that is at most m. So this is order n into m square. Okay, this is just to take the maximum number of zeros you have in every point. While over here, what you have done is you have converted this procedure. So basically, let's formalize this a little bit. What happened for every starting point? We found the max number of zeros to the right for this point x comma y, and then kept incrementing x. Finally, we just report the maximum number of rectangles you can make based on this. Okay, R1, R2, R3, R4. You take the sum for every x comma y. Okay, and the number of rectangles you have to find, like instead of making this order R1 plus order R2 plus order R3, instead we made it order 1 plus order 2 plus, order 1 plus order 1 plus order 1, m times. So what happened then is, for every starting point, that is number of possibilities is n cross m, you found the maximum number of zeros, that is order 1, and then kept doing this for every row. So that is n. So you have final time complexity as n square into m plus order, because we took the sums also, right? Over here is order n, m square. M square. Okay. This effectively, if you have a square matrix, is order n cube. Okay, which is much better than order n raised to power 6 that we had earlier, and much better than order n raised to power 4 that we had before that. I mean, just before this. Okay. I'll just actually take my screen also and take you guys to the sensible part. Can I zoom out? I don't think I can, but I'll write this down again so that things are clearer. This is order n square m plus order m square n. Is this part clear? Like, that's pretty much the question, right? Okay, Leonard has a suggestion. How about we have a cumulative sum of the rows in a separate matrix and then look up the matrix anytime we need it? Yeah, that's true. That's exactly what we did here. Dipanshu Chaudhary, fixing every possible 2 rows and iterating over the columns to find the contiguous block of column of zeros, say k, and then add k, choose 2. Okay, going for combinatorics. Not a bad idea, but let me know if this works. Fixing every possible 2 rows. Okay, so you have this range of rows and iterating over the columns to find the contiguous block of column of zeros, say k, and then k choose 2. Okay, yeah, but then how do you also take the other rectangles which are overlapping with this rectangle, which are like weirdly being created later on? So effectively you have like weird shaped islands, right, of zeros and ones. If you take a contiguous block also, how is it helping long term? It might help in the I was thinking about this for a while. It might help in reducing the runtime, but can it help reduce the order time complexity? I don't think so. So to reduce runtime, there are quite a few tricks you can use here. You can actually use that, like you said, find a contiguous block, and then that contiguous block can just be skipped. Basically, if you are at a position X, a particular column number, right, and you see that the same map is going to be repeated, you just jump up till the minimum point that we talked about a little earlier in this video. So use a priority queue, find that point, and it can help you, but not in terms of order complexity is what I've seen. Okay, we can find max rectangles for something like that. Is binary search solution good enough? So Athar, you're asking, is binary search solution good enough? Yes. So that will give you an order n square m into log m solution, which is much better than n square m square. And it's actually extremely close to the final solution, right? It's just a log factor away. But if you can think about something even simpler. It's hard to say what is simpler. It's more like what strikes you. But if you can chop off that log factor, why not, right? And this is easy to work with also, because there is no sum array that you need to keep. Initially, we were talking about a sum array. We were talking about we might need to use this big ass formula, but we don't need to use it here. Over here, we just have the prefix sums for every row. Right? I don't remember where I wrote that down, but we need the prefix sums of every row. It's the yeah. Okay. Yeah, Akash. That's true. It's a good idea. This can be slightly improved. Okay. So guys, do you have any doubts? For the next 2 minutes, I'll just take doubts. Or if you have any questions in general. Not too many career questions, yeah. It does digress otherwise very often. Anyone has any doubts on how do we find the maximum number of zeros to the right of an element? I think that is pretty obvious. It's trivial. You have to just do a scan initially. For every starting point, find the maximum number of zeros to it, to the right. Till you hit a 1, you just count. So that should be easy. Once you have those counts, what you're doing is for every starting point, you are, for that same row, finding the number of zeros you have. So those are the rectangles of height 1 you can create. Then for the next row, this is very similar to what Nandkishore said. For the next row, you find the maximum number of zeros you have there. So that is height 2, maximum number of 0 rectangles that you can create. And what's happening effectively is that thing is shrinking, as you can see here in the diagram. Every row is shrinking the total number of zeros that you can incorporate in the next height rectangle. Effectively, what happens is for every starting row, for every starting point, you keep heading down one by one and calculating the heights. So the order time complexity becomes order n square into m, because the number of rows is n, and you're doing this for every starting point. Cool. Nitin Bansal is asking how to prepare for system design. It's a very intelligent question. I don't know what to say. It depends on where you are, right? If you're a staff engineer, the resources that I'll suggest to you may not be useful to you. You might already know it. But if you are a fresher, then just go through the system design playlist that we have on YouTube. If you're a person who's currently working in the industry, go for getinterviewready.io. If you are somebody who wants to read a book, you can go for Designing Data Intensive Applications. It's a good book. If you're looking for very advanced system design, or if you are looking for hands-on system design, go for open source contributions if you can do them. There's a link in the description for Get Interview Ready. That's something that I have created. It's my system design course. So I will be marketing it anyways, but in general also I truly believe that it's useful. So if that's the place you're thinking of starting, it's not a bad place to start, but there's a whole channel free content that I've posted. So you can first go through that, right? Okay, BBU, I'm going to be putting your comment ahead. Ncube, fix two columns starting and ending and find the number of rectangles in the section using Cardane's algorithm. Will it work for this problem? Cardane's algorithm. You don't need Cardane's algorithm, right? You can go for something simpler like this. Can we improve the finding max zeros to the right of every cell? I think it can be done in order nm. Although total solution complexity will be the same. How are you going to find the max? Yeah, total solution complexity is going to be the same. Yeah, that makes sense. Yeah, you can improve on that. Doesn't really matter. You can. Okay, guys, thank you so much for tuning in. This has been a wonderful session. I know that this problem is a little hard to actually solve in an interview. It's not that the concepts are extraordinarily difficult. It's actually simple. Okay, and that's the ideal question for any interviewer. They like these kind of questions because they test you not on what you already know, but what on you can. But on the things that you can think of on the spot in a real interview. So all the best, and until next time, then see you. Okay, now how do I? Yeah.